Now that we've done the calculations for some angles, I want to show you how we can apply that to launching a projectile. This time I'm going to launch a projectile at an angle of 45 degrees above the horizontal, and I'm going to look at the opening of the projectile being 1.2 meters above the ground. And we're going to try to predict where that ball is going to land. All right, so we know for the yellow ball that its initial velocity is, we're going to take it to be 6.1 meters per second. And what we're going to need to do is find the initial x component and the initial y component of the ball's velocity. And to do that again, we take 6.1 times the cosine of the angle theta for the x component. So that's 6.1 times 0.707, and 6.1 times the sine of the angle. And it's going to have the same value for both of them. If you take out your calculator and do that, you'll find that it'll be about 4.3 meters per second for both the x and the y components of the initial velocity. So when I fire this projectile in this direction, it's going up at 4.3 meters per second initially, and it's going to the right at 4.3 meters per second, both initially and forevermore until it hits, because the x velocity doesn't change, whereas the y velocity does. So now that we've figured out what its x and its y components of initial velocity are, we need to calculate how long it's going to stay in the air. That's the next phase. So to find that, I'm going to apply the kinematics equations. Everything we've already learned we can use again. All right? So we need to find time to hit. So we need to know what our numbers are going to be. Let's plug in whatever we know is 0. I know that the final position is going to be 0 because that's when it hits the ground. And I think that's it, actually, because the initial velocity is not 0 anymore. It's now whatever I had a minute ago, 4.3 meters per second. All right, so let's go ahead and do our calculation. So 0 is equal to our initial height, which I said was 1.2 meters, plus 4.3t minus, all right, I'll go with 9.8, minus 4.9t squared. Rather than 5, I'll go with this. Definitely need a calculator to solve this. But once I do, I get that my time is, and just so you know what I'm going to do, I'll write it out, minus 4.3 plus or minus the square root of 4.3 squared minus 4 times 1.2 times negative 4.9 all over 2 times negative 4.9, which is negative 9.8. All right, so that's what my time is going to be, and I have to pick my positive root from that. Go ahead and do it and see if you get the same answer as I get. When I do the math, I get that time is either 1.1 second or negative 0.22 seconds. I take the positive root. So it's going to take 1.1 seconds for my object to hit the ground. How far is it going to go during that 1.1 seconds? So I want to find the final x position. And if you remember, the final x position, because x acceleration is 0 and the initial x position we're taking to be 0, final x position just becomes the initial x velocity times the time. Well, we know the time, that's the 1.1 seconds. The initial x velocity was 4.3 meters per second. If we multiply those two, we then get 4.73 meters, nearly 5 meters. That's what we're going to see. We're going to see if it lands at that distance. The other thing I want to point out, though, that's of interest and will be part of the demonstration here is, where is the highest point going to be? And what is the highest point? In other words, can I safely stand under the projectile being launched? That's what I'm going to do. I'm actually going to do a demonstration where I have somebody else fire the projectile, my daughter, so we can maintain We don't have to worry about the social distancing exactly. And we'll figure out if I'm safe where I stand here, and then we'll see if indeed I am. So how would I go about that? So I'm going to find the highest point. How do I find the highest point? Well, I'm going to find the time of the highest point. So I need to find the time of the highest point. So I could do it this way. I can say, well, at the highest point, VF equals 0 at highest point. All right, so if that's true, I can say, okay, VF equals V initial minus G times T. And this is, of course, the Y information here. The final Y, this is true at the highest point. The Y velocity is 0. The X velocity is still going to be 4.3 meters per second, but the Y velocity is going to be 0. So I can then plug in my 0 and say 0 is equal to V initial Y minus GT. And I can solve for T. T is equal to V initial Y divided by G. All right, and the initial Y was 4.3 meters per second. G is 9.8. Do the math. You're going to get something a little less than a half, but I'll do that. All right, if I take 4.3 divided by 9.8, I get 0.44 seconds. So at 0.44 seconds, that's when my object is going to be at its highest point. So how can I use that? Well, I can now plug in .44 seconds into that equation to determine the x position of the highest point. So I have 4.3 meters per second times 0.44 seconds. And that's equal to 1.89 meters. So that's where I'd want to stand to try to avoid getting hit by this projectile. And how high is the highest point? Well, I can plug the 0.44 seconds into this equation. Whoops. Notice that on my initial velocity, I'm specifically saying it's the initial y velocity rather than the initial velocity, because that could be confusing as to whether I mean the x velocity or the y velocity or the vector, sum of the two. But it's specifically the y velocity I'm interested in to find the y highest point. So go ahead and plug the numbers in, see if you can get it. I'll do it, and I'll give you my result too. I plugged it in and got 2.14 meters, which is great because I'm not 2 meters tall, so it should be comfortably over my head, even with error bars. So if I stand in the right place, here's what should happen. If I stand in the right place, what we calculated was, here's my projectile launcher. It's launching this ball. It's going to land, we said, boy, it's ancient history now, but about 4.73 meters away is what we came up with. So that's 4.73 meters. It's going to take 1.1 seconds. If I had a stopwatch, I could time it, but it's hard to time times that are that short. At 0.44 seconds, it's going to be at the highest point. That highest point is going to be about 2.14 meters, and it's going to happen, we said, got to check that too, it looks like 1.89 meters away from the launch point, if I recall. Yeah. All right, so that's for a 45-degree launch angle for the yellow ball. I'm going to do the same calculation for the glass marble and see what I get for that one. But I'm also going to mark up my floor with everything so I know where to stand and I know where to expect the ball to land. And we'll try it out.